Thanks for joining us early today. You've still got time to go and make a drink before we begin in about 5 minutes' time. As always with Doulos webinars, all attendee microphones are muted throughout the broadcast. However, the webinar is interactive. We have expert technical staff on hand to answer your questions by text during and after the presentation. Please keep an eye on the questions and chat tabs in the GoToWebinar interface and enter any questions you have as we go along. We'll start in a few minutes. Welcome, wherever you're joining us from, particularly if you've not come across Doulos before. We'll be starting in a few minutes. Okay, the webinar will begin in a minute or so. Before we do, I'd just like to thank our webinar partner, NXP, for their promotional support of this event. Our subject today is performance profiling on ARM embedded systems. Allow me to introduce our presenter. David C. Black is a lead member of the Doulos technical team in North America. Based in Austin, Texas, his expertise and experience span the domains of design and verification of complex system-on-chip systems, and his knowledge covers both hardware and software design techniques. David is an expert instructor in ARM processor technology, including the latest V8 processors. He regularly delivers training for system integrators and software design teams, developing ARM-based systems at locations around the world, and he's an ARM-accredited engineer. Please do keep an eye on the questions and chat tabs in the GoToWebinar interface and ask any questions you have by text as we go along. That's it from me. Over to David.
Thank you for that kind introduction. Well, folks, hello and welcome to this webinar on performance profiling on ARM embedded systems. My name's David Black, and I will be your guide over the next hour. I'd like to make a quick nod to copyrights, trademarks, service marks, etc. for all the companies that may be mentioned during this presentation. Let's get on and discuss the agenda. So first up, I'm going to be discussing what is the problem that we're attempting to address in this particular webinar. We'll then move to do a short discussion on some aspects of methodology and talk about approaches to solving the problem. We'll also talk a little bit about some of the pitfalls, and then I'm going to spend a fair amount of time showing a couple of examples of techniques to extract the information that we're looking at, that is to say, profiling information related to performance. We'll wrap up with a summary as would be expected. So let's get on now and take a look at the problem. And the problem is performance. So what is that problem? Well, the definition of performance is something that we need to understand, and it depends highly on your target's goals. Generally speaking, when we're talking about embedded, and that is part of the focus of this talk, we want to talk about the idea that there are real-time requirements, deadline requirements, and if your product is not meeting those requirements, then performance may be an issue. There are also non-critical elements that compete with whatever's left over, and they may not be performing adequately for your design needs. So there are hard deadline requirements, and then there are the softer things, but overall you will need your product to perform in an effective manner. Power consumption may be an aspect of performance that we're considering, and we want to minimize that so that we can make better use of our batteries, or perhaps also on another area, reduce heat being produced by our products. We want our communications to operate smoothly, and that operates on several levels. Communications can simply be the communications between an internet communication from our device back. After all, a lot of our embedded designs are IoT. Communications may also refer to operating smoothly things like voice recording or voice playback, video, and so forth. Minimum memory footprint may be an aspect of performance that you're concerned about. That's really not a consideration, particularly for what we're going to go over. But sometimes when people talk about performance, they think about that. So I wanted to just highlight that that is something that some people talk about. It is not our focus. So again, what's the problem? What's the performance issue? Well, the performance issue is oftentimes a need to improve the performance. For example, it may be that your product at the state where we're encountering this problem doesn't meet your requirements, doesn't have enough headroom to make you feel comfortable. It might even be dangerous from a safety perspective if there's any chance that it would not meet it, particularly when we talk about those hard deadlines. So that one is a biggie. It also may be that there's some observation of intermittent failures correlated to workload, and so understanding the performance, maybe we can figure out what the problem is. It may be a technique to debug issues in the design. Or it may just simply be frustrating for the end user that the product is basically behaving, it's too slow. It doesn't, for some reason, that we need to think about how we can improve the end user experience. And then lastly, maybe you just need to outdo the competition. Sometimes performance is an issue of being able to have a new product bullet. Maybe it's this one is faster than the previous version, or it's faster than all the other guys out there. So that's a general idea. But when I talk about performance, I want to do a little bit of focus here now on profiling. The idea of profiling is basically measuring the software function versus the time or perhaps power. Now, power is not going to be a focus of this discussion, but I did want to mention power because that is sometimes an issue. Software function usually means named subroutines. In other words, they're identifiable in the software as code subroutines, and we are often coding are embedded in either C or C++. The concepts being discussed here could equally apply to other languages, for example, Python. The reason that we measure, by the way, versus time, because time is indicative of speed, right? When we talk about performance of some software, how fast does it perform? And that's a speed of computation or functionality. And when we talk about power, that also relates actually directly to this whole time idea, because the time spent executing code plus the clock frequency determines the amount of power that's actually dissipated. All right. So let's talk a tiny bit about some methodology aspects of this. First off, if you're going to say you have a performance problem, then you want to understand what it is that you need to accomplish if you were to meet that performance goal. You need to understand your design requirements. That seems an obvious kind of thing. But you need to also, if you're doing performance analysis, you need to understand the interactions between the various tasks, subroutines, if you will, interrupt service routines, and so forth. And it would be helpful to have things like UML components, sequence, or activity diagrams to help in that understanding. So one part of the methodology is to make sure you can identify what it is that you need to deal with, and then think about what it is you need to measure in order to decide what's going on here. So are we actually measuring throughput, latency, load, error cases? How do some of the overheads, there are some overheads that are inevitable, so synchronization or switching overheads contribute, and we need to be able to understand that well enough that we don't confuse the operation of a subroutine with the overhead that needs to get there, or we need to understand maybe the need to reduce that overhead. We also want to be careful to focus on what the specific issues that we're trying to solve. Are we missing deadlines, sluggishness, etc.? So these are things that we want to think about as we're approaching the problem of profiling. Okay, and then finally, we need to know our tools that we're going to use in dealing with this. So please, you obviously should be reading your documentation for the design, but also the device, the processor that's in that device, and the tools themselves. And if you don't know your tools before you go into this situation, you're going to have some real frustrations. Really, you need to learn these before starting your project. So education on your tools is equally as important as an education on the design problem that you're being faced with. But even just understanding the device and the processor. At a hardware level, you're software designers, but you need to understand this at a hardware level. This is not a simple topic. So let's talk about profiling now. Let's talk about approaches to profiling. General purpose I/O is a poor man's approach to measuring performance. If there's some spare I/O available, you can simply use a logic analyzer, and then somehow in the software you would set things to basically set that general purpose I/O high and low depending on where you are in the software, and you can use that to measure things. But we need to go beyond that. Another approach that's commonly used in software, often taught in schools, is software instrumentation, using things like the GNU GPROF profiling software. But it's quite intrusive. It modifies execution by inserting code into your existing code as a way of measuring whether or not you get to particular subroutines and how often and so forth. So generally that's not good for a real-time, and most embedded have a real-time component. So I'd say both of these are not exactly the best way to go about dealing with profiling. A slightly better way is the operating system supported. For example, perf in Linux. If you have a large embedded device and you're dealing with threads or processes, then there are operating systems calls to the hardware support that's provided. So this is a little bit less invasive. It is somewhat invasive, but it's using an underlying hardware architecture. And that's really what the focus of this talk is on, is that if you're dealing with embedded and you're dealing with ARM processors, then it turns out that ARM has hardware support for dealing with the profiling. It's part of what they call their non-invasive debug architecture. They have internally, basically, they have little counters to count numbers of cycles, count a number of different features in the processors. It's very dependent on the ARM core. They also have features to do instruction tracing, sometimes data tracing, and so forth. Of course, all of this requires some amount of software support as well. So it's not like all of this is completely non-intrusive, but there's got to be something. For example, we may just need an external debugger. Let's take a look at the ARM debug components a bit more closely. So you have your debug terminal on the left, and we have an ARM core on the right here inside our SoC, and we want to communicate with it. And ARM provides, when you talk about an ARM core, you're usually thinking about just the processor, but there are a number of optional blocks. By the way, not all implementations provide these. It really depends on your silicon vendor. You need to look this up on any given SoC, right? And there are multiple ways to connect to these, right? And they're actually very much dependent on the SoC and probes. So let's take a look at that a bit. So usually we'll use USB to connect to our debug station, typically a laptop, maybe a desktop machine. And that debug probe will then talk to a debug access port, which is highlighted with 1 here on this diagram. And the idea of this is to allow our debugger or our software, this is the software support that I was referring to earlier, to communicate with the SoC, the ARM core. And internally, this core is all hooked up with something known as ARM's CoreSight architecture, which CoreSight is simply the trademark for the technology ARM uses to do debugging, tracing and profiling, and all the things that we're going to be talking about here. So what we do see on the right, by the way, are a bunch of blocks. They are optional blocks, by the way, of the SoC, as I mentioned before, from ARM, but they are quite common. Things like a really common one would be the breakpoint unit, the BPU that we see here, or a little bit more extensive would be something like the embedded trace macro cell, that ETM there, which will provide us with a lot of great information. On the far right, we have something known as the embedded trace buffer. We won't actually see an example of that today, but that's it's part of one of multiple approaches to dealing with tracing information. Then there's the instrumentation trace macro cell and the data watch point trace unit here. And then finally, that last little acronym, just getting those out of the way, the trace point interface unit. So these things hook up variously, and so what I got shown here is that you may have a JTAG, or what's known as a serial wire debug, which is used to control and observe things going on in a core. There's one other component though, and that is the trace, or sometimes a serial wire out information to get the trace data out of the processor. That is actually a separate bit of I/O, but generally they talk to the same kinds of probes. They'll comment on the probes. There's a whole variety of probes that you can obtain. Sometimes if you buy a development kit, it will come with an onboard on the development kit. You will find that they've actually implemented, if you effectively, a probe on the board, usually with a USB connection to it. However, a lot of times these probes are somewhat limited. The focus here is on the SoC, and the probe is there simply to try and gather the information. So you may want something a little bit more powerful. Companies like Sager, well, actually ARMS, Sager, variety of different providers have their own external probes. What I'm showing here on this little picture, what we're going to use in the example today, is the Sager JTrace probe, which is a high-end probe for doing both debug and trace. And trace is not always supported by all of the different probes, or supported at different levels, if you will. This is just a higher end of that. I'm going to talk a little bit about some of the pitfalls of profiling and tracing. Sample rate is something that you need to consider. It has to be set up correctly, otherwise the software won't work at all. But then it can be set up to sample at slow or fast data rates, and the data rate does matter because it might falsify results if you're not getting enough samples to see what's going on. On the other hand, if you get too much data, you might feel a bit overwhelmed. In terms of pitfalls, don't get distracted. If you've got a problem, try to focus on the functions contributing to the issue. Sometimes it's not obvious. Sometimes the functions that we discover that are causing the problem are not directly related to the issue. So again, it's a hard thing to deal with, but you need to be aware of it. Try to focus as best you can as you deal with it. And also understand that hardware architecture will affect results. For example, cache is becoming a little bit more common on some devices now. We won't look at that today, but if there's cache involved, you need to get educated on the effects of cache on your design. It's not all about your C code or your C++ code. The hardware can have some strong effects on how that code behaves in the environment. All right? Might even make observation that your compiler switches affect things as well. And then another pitfall to be worried about is the reality of the environment that you're either profiling or tracing. You want to make sure that you're actually profiling and tracing the full code set, including your RTOS or what other extras you have out there. When you think about the product and say, I've got a problem with the product, it's with everything running. So you can do profiling and tracing, obviously, on just small standalone functions, and that may be useful for sort of fine-tuning them. But at the end of the day, you need the full code set, and you also need to think about the input data sets and the environment in which you're testing. If you just create a data set to test a particular feature, you may be missing out on what the real product environment is. And so you want to think about how what you're tracing and profiling relates to the real environment. You also need to, in some cases, you may be setting up for error cases, and that's fine. Just make sure you have a good understanding of how that fits in. So these are just some general things to consider as we look at the profiling results. So let's get on with the example for today. And our example, we're going to use an NXP MX RT685. And we're using the evaluation kit from NXP. And this is just part of their RT600 series of processors, a high-performance processor. This particular processor is a heterogeneous core. It consists of an ARM Cortex-M33 with the DSP, and also has crypto co-processors on it. But it also, there's another core on there, which is the Cadence Extensa Hi-Fi 4, which is a DSP engine. Deals particularly well with things like audio sampling and so forth. We're not going to focus on the second processor. Our focus today will simply be on the ARM Cortex-M33, but I will point out that they're tied together in the debug interface, and certainly profiling and understanding performance in that area is also something that needs to be looked into. So our focus is on this chip, and when choosing something to use as an example for this webinar, I particularly like this device because I looked at the debug specifications, and they indicated the optional elements of that ARM provides were supported, the ones that are needed to understand trace. In particular, the embedded trace macro cell, the instrumentation trace macro cell are there. Some other components that are listed here, the breakpoint unit. Obviously, breakpoints are useful. This is hardware breakpoint, so not software, so it's a special consideration that you probably want in your SoC if you can get it. The cross-triggering interface, we won't use it, but that would be a way to help when debugging across cores. It's the idea that you can have debug a breakpoint, for example, in one side, cause both cores to halt, or allow one to continue while you're only debugging one, and maybe there's not, the dependency is not there that you care about it. And then, of course, if you're going to deal with tracing, you need to have a design, an SoC that brings out the trace signals that tracing is, and so there's a special trace interface unit, trace port interface unit here, right? So we've got on this board, we actually have a 20-pin debug connector with trace pins, so this is good. We can use that with our JTrace from Sager. Just look a little more deeply into the manual. So this is one of the places where I was just confirming that what they're talking about here matches what we need. I've highlighted on this diagram. This diagram comes directly out of their user manual for the device, for the SoC. And what I've highlighted here are the ARM components. In particular, you'll notice here, so we have the serial wire debug. This is the external connection to deal with the debugging itself. And then we have the Cortex-M33, and you'll notice that debug interface actually talks both to the ARM processor and to the Hi-Fi, and there's even a debug mailbox down in here. When again, those are kind of out of scope. And then inside the M33, you see these are all debug elements that ARM's CoreSight talks about. If you want to learn a lot more about these topics, and I really recommend you do, if you're using a processor and it has special debug features, it's always good to know what they're capable of doing so that when you encounter situations during design, you know what your tools are up to or whatever. Notice on the far right there, we have outputs of, we have actually 5 signal outputs, a clock for tracing, and then 4 data bits. So that means that the processor, this particular case, it can output a fairly large amount of data. If it only had the serial wire out interface, you'd have a lot less data. It has both, and that's kind of useful for our investigations. So now let's proceed into our demonstration. So here we are in the NXP's free MCU Espresso IDE. Now this particular one I'm running on a MacBook Pro, in other words Mac OS. It also works under Linux, and it works on Windows, and it is essentially the same interface. They've kept these up to date quite nicely. So what I've got here is a sample project. It's just my little profiling project. It's based on a simple GPIO example project that you can bring in from the IDE. And the MCO Espresso itself is an Eclipse-based tool with a number of plugins. Probably one of the nicest parts of what they did with their plugins is they have this quick start panel that enables you to quickly get to business. If you're not familiar with Eclipse, then this might be helpful. So I've got the code here. I'm going to go through some steps here. First thing that needs to happen is what we're going to do in this example is I'm going to turn on profiling and show you how you can get a little bit of information with profiling. So the first thing to realize is that the output for profiling comes from the serial wire out port. That needs to be configured. We need to do some settings, if you will, on the design. So if we go down here, the lower left, you can see there's these MC Espresso config tools. So there's open pins. We're going to go in and configure the pins here. I'm going to briefly look at the clocks, but these are the two things we'll kind of focus on, mostly on pins before I go and execute the code. You can also get to these in the upper right. So if you're not familiar with Eclipse, the upper right here, we have some icons. They actually match what was down in the lower left that correspond to what Eclipse calls perspectives, and he simply changes the view of what's on the screen here. So I'm going to use I'll enter from down here under the config tools, open pins. And here we go. We have basically a very nice diagram of the pinout for this particular device on this particular board, which is the EVK for the RT685 device. And what I want to do is I want to focus on the serial wire out. So there are a lot of pins on here. And you'll notice some of them are in green. Greens are pins that are configured, but we want to make sure that the serial wire out port is configured. So I just typed in SWO up here for that. That's the name of that particular pin. And I notice that the SW out line here is not enabled. So I go ahead and click on that. And it says, okay, what function do you want on that pin? So typical to a lot of SoCs that you can acquire, they multiplex the pin for different functions. So hopefully you're not needing these other functions when you need SWO. There's other places that could come out as well, but here's the primary one here. So go ahead and select that, and on the board it actually is routed to the connector that we're going to use to do the debug. And I go ahead and click done here. And now, assuming that's all I need to do, in this case it is, I'm simply going to say update the code, and it's actually going to change the source code for the board to configure the multiplexing of pins, the outputs, which is what we just told it to do. And so now we've come back to the default development perspective. And you'll notice in the upper right that the perspective it is highlighted up here. And so you can tell between the debug perspective or the pins, which is where we were a moment ago. Now, something else that you sometimes have to worry about, and I'm just going to show you, we'll go here through the upper right, is the clocks and how to configure those. And the way you configure clocks in here is you can come in and you can simply click on these things and select different routings for the clocks on the system. And again, this then will update the board clock logic files and so forth. But we don't need to do that, but I'll just make an observation here. So we have a main clock up here in the right here, and then up here on the right you see the trace clock. So that trace clock will also be important to understand when the device is collecting data using the trace interface. That's important to understand, trace and debug. And so that's just something worth noting here. Okay, we'll go back now to the development environment, and I'm simply going to build a project, and then we're going to debug it. Now, you can do this in one step or two. You can click on build, and that's how I'm going to go ahead and do it. But if I had clicked on debug, it would have actually just determined that it had not yet been built. It would build it, And then I click on debug, and as I click on debug, I'm now going to move into the a different perspective for debug purposes, or it's going to reset up things here. So let's let that settle in. And it only takes just a few seconds for that to actually happen. And let's see here. We're okay. So you can see that when it comes up and debug, the default for the debug configuration is to bring it up to the first line in main, and you can see that here line. So before I start running the program, and all I want to do is run the program and gather my profiling, I need to turn on the profiling features. And so what I can do here is I can select an analysis, and I can go take a look. First I want to look at the configuration, so let me bring that up. So I've got this serial wire out trace configuration. We're actually using semi-hosting in this project in addition to doing the tracing of things. And so we're going to be using the instrumentation trace macro cell, which has a port 0, it turns out, is used for most of this information. So that's by default enabled. I don't need to change anything on this config, just bringing it up to show you. You can see here clock speed. This is that trace clock that's coming in here. You can also decide if you want to sample less frequently, you can actually change the sampling. If you want to sample over a longer period of time and you don't want the counter to overflow because you're leaving it for a long time, you can change that. All right. And then there is some additional status about the connection. We don't need to worry about that right now. I want to go over to the serial wire profile, and you can get to that through this menu, and I already actually had brought it up earlier, so it actually has a tab, but it would bring up a tab on here. I ended up moving it up here. I like this position. It gives me more visibility. By the way, you can resize all these frames or whatever. Some of you may be familiar with the tool already. All right, so now I'm ready to get started on doing execution. Except that I have to turn on the profiling. So let me click now this little green data display button here in the SWO profile. Now I am ready to proceed. So what's going to happen now is I'm going to go ahead and press continue in the upper left, resume, also F8. And when I do so, we're going to see data being collected. It's just going to start executing on the board. I'm going to see an LED flashing. So I just pressed resume. Now you can see over here, every time it takes a sample, it's adding it up. And what's happening is it's sampling the program counter, the hardware in the ARM processor for this design. It's actually the embedded trace macro cell has actually got a counter sampling, and it's sampling the program counter, providing us those samples at regular intervals. And what we're doing is we're accumulating, for each sample, where in the code we were executing, which function were you at. And here you can see this is a percentage of how many times we're executing things, so cumulative samples. If you stop this and run it, you can also look at the current samples. That's not as interesting to us, really. Now also look at the code coverage in here as well. So you can get an idea of how much of your code is being properly covered here. You can see some functions are getting covered more than others, get more fully executed, if you will. All right. I've got a timer in here for the SysTick timer, and the ARM processor is a built-in timer across all ARM processors in the Cortex-M family. And you can see it's executing a lot, but it's not taking very much of the time. More of the time is being spent in other activities up here. Notice this, we got 18% on this reset and clear. It's kind of interesting. Why are we resetting and clearing? And so if we were interested in this and we started to do it, by the way, we don't need to continue to run with. Let's just stop I'm going to pause the code, and so now it's paused inside the function here. But I'm kind of curious what's going on. So if I double click on the name of the function, it actually brings me in the source code directly to the function. I can look at it, try to understand, clears a peripheral reset. I wonder what's going on there. So the next thing I might want to do is look at who calls this function, because somebody's calling this repeatedly. And one of the nice ways we can do that is we can go to let's see. I believe you can do what's called a call hierarchy call here. So here it says peripheral reset, but the way I get to this is I'll go over here to the outline and this is an outline of whatever's in this tab over here. And I'm going to do a right click on here, and I'm going to say open the call hierarchy. And then down below is the call hierarchy. And so what it shows me is there are two different ways I can do the fan in, who's calling me or who do I call. So if I click over here, it says that inside here there's an assertion failed call. And we should be able to just kind of scroll down through here and see that within here somewhere there's an assertion fail. Where's the assert in this piece of code here? Right, it's right here on line 106. All right, but let's look at the fan in, because what we want to know is who's calling us. And if we look down here at the little triangles next to these, I can expand these to see that, okay, reset and clear peripheral reset is called by the reset peripheral reset, called by board and params, and take a look here. So there are a number of different places that that call it, and apparently GPIO port init hash crypt looks interesting. GPIO port init, well, we call that, but in our main code, if we go back to the main code, we'll observe that board init pins function gets called. Let's see, go back in here from main. Oh, GPIO init called it, and the board init pins gets called. And so those don't look suspicious since they're being just run once before we get to the main loop. And then we look down here and see this cache script, which calls something called odd compute. That's odd compute, which is in main. So where is that in here? If we double click here, we'll see where odd compute calls it. If we double click on main, we'll see where odd compute's being called, and it's in the main loop. Every time around we call odd compute, and then if we go in and take a look at what's in odd compute, we notice that we have a large loop here. This was intentionally put in here just to make this thing highlight. And then it's calling hash crypt init and dinit, and we might at this point realize there's something maybe wrong at this point. So that's just a simple example of maybe some of the analysis you'd undergo. But realize too that when you're looking at this profile and you're thinking about how things are executing, you ought to be able to make sense, if you understand your code well enough, of why certain things have high percentages. So if you had known more about the code, you might have said, oh, this is just normal, that was understood, but maybe not. And so the idea is to kind of get a better sense of how the code is executing. All right? So I hope that was helpful to talk about profiling. And so I would like to conclude in summary that when talking about the notion of profiling, you need to understand what's measured. Don't skimp on the tools. The tools make a difference. You can perhaps see from the demo there were different aspects of the tools you may want to consider. And when I talk about tools, our tools are both hardware and software. Generally speaking, tools are worth paying for, both the software tools and the hardware instrumentation on the outside. So the built-in probes on your evaluation kits, those are useful, but they sometimes miss areas, or when you get to your real product, you're going to want to be able to apply the probes directly to the real product. And so I recommend you consider looking at those probes carefully when doing the design, and then also get appropriate software for the debug. Don't just go for the free stuff. You're making a commercial product. You're going to be making commercial profit. You need to invest. All right. And when we talk about investing, also need to get educated and practice with the tools that you're talking about. So that education extends from really understanding the processor architecture, all the way to understanding the tools involved and how to apply those to do the debug. So thank you for attending. Here I list a few simple resources. We'll make these available in the chat window. You may also find on our website, Doulos, we actually have a know-how section where we can focus a little bit on some of the ARM products, for example. So this presentation was on the ARM, the Cortex family of profiling features and so forth. ARM also has a support library. Again, if you take some courses from us, to get some hands-on learning, if you will. Even in the online context, we have some training with pretty effective hands-on experience with the various things that you need to understand. And we have courses for all the different ARM Cortex components. The Doulos, by the way, is more than just an embedded software training house. We also teach things like SoC design and verification. We do FPGA and hardware design, of course, the embedded software, and even Python and deep learning. So I highly recommend that you might want to check us out if you are into any of those things and need some more education, or if you know some coworkers maybe that are struggling with some aspect of that. Thank you for your time. Observation, if you have some more questions, hopefully you've been putting some texting some questions in during this webinar while I've been talking. But if you haven't, please take a moment now to ask your questions in the Q&A dialogue. We will try to answer them in the available time. If there's not enough available time to answer your question, it will be answered offline and then be emailed to you after the webinar. Thank you for your time.
Great. Thanks to David for that presentation. Thanks to you all for attending today, and thanks to our partner, NXP, for their promotional support of this event. We'd be very grateful for your feedback on this presentation, so please could you use the exit button on the GoToWebinar interface when you leave today and complete our survey. If you are looking for further related training, you might be interested in ARM Cortex M23 and M33 software design, developing with ARM Cortex M online, or ARM TrustZone M for Cortex M23 and 33 online. Links to the full course descriptions are in the chat. You can also check out the full breadth of Doulos's ARM-approved training courses by visiting doulos.com/ARM. All Doulos training can be delivered in person, live online, or as on-site team training. To browse the complete course portfolio, please visit doulos.com/training. Feel free to use the last question of the exit survey to get in touch with us to further discuss your specific training requirements, or to request further details from NXP about their IMX RT crossover MCUs. We're going to stay online briefly to answer any final questions you have about today's presentation. If you're unable to wait around, we'll do our best to answer your question and include it in the Q&A log, which we'll send you along with a link to the recording of the webinar within the next few days. Many thanks again for attending today.